All right, in the second half of our lecture today, we're going to look at this idea called statistical independence. So as always, let's take a look at an example here. Example is Russian roulette. Suppose, what's one of the elite clubs on campus? A marketing club? That's a good one. So you want to get in the marketing club, tough club to get into, and you have to play Russian roulette 4 times to get into the marketing club. All right, so what happens in Russian roulette? Let's assume we have a 6-chamber gun, 1 bullet, and there's 2 ways to play Russian roulette. I try to get my brother-in-law to play it this way. You go click, 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 click. That's one way to play it. And the other way is to spin, click, spin, click, spin, click, spin, click. But my brother-in-law is too sharp for me, and he won't do either, but he would prefer the second way over the first for obvious reasons. So let's let B equal bullet in the firing chamber. And let's what's the probability that any try of Russian roulette you're going to have a bullet in the chamber? 1 out of 6, right? And what's the probability no bullet in the chamber? 5 out of 6. So you got to survive 4 trials of Russian roulette in order to get into the marketing club. What's the probability we will be elected, not posthumously, into the marketing club? We will survive if what happens? First spin, no bullet. Second spin, no bullet. Third spin, no bullet. Fourth spin, no bullet. And all of them happen simultaneously. The first no bullet and second no bullet and third no bullet and fourth no bullet. Then we will survive to get into the marketing club. Right, so now, this spinning that we do between trials, this gives us what's called statistical independence, meaning that each try is statistically independent. Knowledge of whether there was a bullet or no bullet in there on the first try tells us nothing as to whether or not there will be a bullet in there on the second try, or the third try, or the fourth try. The probabilities remain the same. Okay, so statistical independence is something that doesn't happen very often in business, because in business, most times we're doing things that are related to each other. We found that that our advertisement, if you saw the advertisement for our cookies, you were more likely to buy the cookie if you were male than if you were a female. So it changed the rate of cookie purchasing from males to females. It was twice as high among males as it was females. So those are not independent. And whether you pass the exam in the second problem or had an MBA, those probabilities changed. They didn't change a lot, but they changed some. So those are not statistically independent. But when we do the spinning between the trials, what it allows me to do is to remove intersection sign by taking the product. So independence allows me to remove the intersection sign by taking the product. And we'll show that the form in a minute. So what's the probability of us surviving to get into the marketing club? 5-6 on the first try, 5-6 on the second, 5-6 on the third, 5-6 on the fourth, and 5-6 to the 4th power. Okay, on an exam, this is the only way you'll ever leave it. Do not ever multiply anything out in here. It's about 50%, 0.48 chance that you'll make it into the marketing club alive. All right, so what is this idea of statistical independence? Okay. There's 2 ways to illustrate it. Here's the way we use it. Okay. If I need an intersection, I ask myself, are these unrelated to each other? Are they independent? Are we looking at the whether the temperature went up or down today and whether the stock market goes up or down today. They're nothing to do with each other, right? They're statistically independent. If so, then I can remove the intersection sign by taking a product. If so, and only if so, can I do that. The equivalent statement of this is, however, the probability of A given B is unaffected. It is the same. It is exactly the same. Okay? It is exactly the same. Knowledge of whether or not B occurred does not change the probability of A at all. It did not change them whatsoever. The probability of A means unaffected. So whether the occurrence or non-occurrence of one event tells you nothing about the other event, then they are said to be statistically independent. In Las Vegas, or your friendly Indian casino, we have a number of games that are available to play. Some of these are games of chance. They have statistical independence, and some of them are games of skill. They do not involve statistical independence. So if you take a notepad into the casino and write down whether red, green, or black comes up on the roulette wheel for a couple hours, are they going to care? Does the casino care about that at all? They don't care at all. You want to come do that? That's fine with them. You want to take your notepad over to the crap table and watch, whether a 7 or a 6 or a 5 or 11, watch the rolls come in and keep track of them for the last couple hours. Do they care about that? No. Do they care if you go to the Keno area, or does the California Lottery care if you keep track of the numbers? And every once in a while they publish the numbers that have occurred most recently a lot, with high frequency. And then every once they also publish the ones that haven't popped up yet. And there's two schools of thought. Some people say, oh, I'm going to play the ones that are hot. And then the others are saying, I'm going to play the ones that are due, right? Great, knock yourself out. Doesn't matter at all. Could care less. Casino could care less. California Lottery could care less. Slot machines, the idea of let's wait till somebody pours their entire week's wages into the slot machine, and then when they leave it, I'm going to jump on it because it's due. Okay, you want to do that also? Great, no problem. They have no problem doing it. With you doing that, no problem whatsoever. However, if you take a notepad over to the blackjack table and start writing down the cards that are coming off this deck, what's going to happen? If they're nice to you, they'll kick you out. If you cause a problem, they're going to have a little chat with you back lot. And they won't be so nice about it because this is a game where we have statistical dependence. The whole idea of counting cards is, what's left in the deck is changed by the cards we've already seen. Probabilities change, okay? And so blackjack is a game of skill, and you can count cards and wins. It's way too much work. I don't do it. You can't, it's hard to count cards when you've been drinking. I've heard about that. And poker, of course, there's a lot of luck involved in poker. To win a tournament, you got to get lucky, but there's a lot of skill involved also. I'm an avid poker player. Luckily, I didn't find out about poker. It didn't become popular till I was, older, so I wouldn't spend my youth as a poker player. But I'm an avid poker player because it's a fun game. It's very frustrating, but in the long run, the better players do much better than the unskilled players. All right, so we have the idea of statistical independence in roulette. Every spin of the wheel, history is erased, correct? Every craps, they shake the dice, okay, that erases the history. They throw the dice, and erases history. You forget about it. The history is worthless. That's what statistical independence means. However, in blackjack and poker, as those cards are dealt, those probabilities are changing dramatically, okay? And it's up to you to, like in poker, you keep track of, you refigure your pot odds, your odds of winning the hand given what you got. And as each card is dealt, those pot odds change. And you got to figure out whether you're getting the right payoff to warrant your wagers. We also have this idea of the law of large numbers, which I'll talk much more about next time, and the law of averages. First off, there is no law of averages. It does not exist. There is no such thing. The only thing that does exist is the law of large numbers. The lay person, you hear, people walk up to the crap table and they say, how's it going? He said, geez, this guy's held the dice for 30 minutes without rolling a 7. And the person says, well, I'd like to start betting on him, but 7s do. No, not at all. Okay, or you've watched a roulette. Reds come up 20 straight times. Where's all the money? A lot of it's on black or green because they're due. And a lot of it's still on red because it's hot. Okay, if your idea of the law of averages is after 20 straight reds, black is due, and you got a large wallet and we'll play it, they'll come they'll send a plane for you. Okay, because if that were the law of averages, you could go to Vegas and win consistently at roulette and craps. Are there any professional roulette or craps or keno players? No, none. Zero professional, because you're going to lose that in the long run. All right? Are there professional blackjack players? Yeah, the movie 21 with the group from what college? The movie. I forget which one. Which college was it based in the movie? Nobody knows. Okay, that's your homework. Check that movie out. And in poker, are there professional poker players? Sure, there's tons of them. All right, so let's do an example here. Anxiety Airlines is a low-budget airline servicing smaller volume routes using World War II surplus airplanes. Anxiety's motto is, we put the fear back into flying. Yeah, I like that. You're on board one of their airplanes that's coming in for a landing approach. The airplane has 3 different independent systems for lowering the landing gear. And when we do backup systems, like the electricals in a hospital and so on, we make them statistically independent because that makes the reliability the highest possible it can be. Statistically independent backup system. So if one fails, it doesn't tell you anything more about the other one failing. The first system works 80% of the time. The second works 70% of the time. The third 60% of the time. What is the probability that the landing gear will be lowered? That is to say, at least one of the systems will work. So notation, let A be the event the first system works, or S1, or any letter you want. Let's B be the event that the second system works, and let C be the event that the third system works. And those are the probabilities we're given. So on the exam, you set up notation, say what am I given, and then what am I asked to find? What's the probability the landing gear will be lowered? It'll be lowered if the first system works, or the second system works, or the third system works. If any of those occur, I'm in good shape. So what is this? So here's the A area right there. Here's the B area right there. Here's the C area right there. And as long as I'm in anywhere in that darkened region, the landing gear will be lowered successfully. We do not have a rule which goes for the union of 3 events. We do have a rule that covers this case, however, and that is Rule 1. Look at the complement. Look at the opposite. What's the opposite of the landing gear will be lowered? The landing gear won't be lowered. You're screwed. The landing gear won't be lowered if the first system fails. What? And the second system fails. And the third system fails. Then you're screwed. So, in order to solve this problem, I'm going to go 1 minus probability that the landing gear will not be lowered. And now, whenever I see a series of intersections, I ask myself, are these events statistically independent? Because if they're independent, I can remove this intersection sign by simple multiplying the events out individually, the probability of the events individually. And yes, the problem did say they were statistically independent. So be very careful of your use of statistical independence on the exam. Make sure that it's your assumption that these are independent is warranted, that these events have nothing to do with each other, that the fact that the first system failed, that they share no common components together, and on an airplane it's virtually impossible to get systems that are totally independent of each other. But the problem says it is, so we'll go with it. And the events have nothing to do with each other, so then I can remove the intersection sign by taking the products. So 1 minus probability of A naught, which is 0.2, B naught is 0.3, and C naught is 0.4. On exam, that is the answer. Do not do any more than that. That is more than sufficient. You say you want to practice? Well, ask and ye shall receive. Here are some practice problems for you. Page 2, number 4, page 3, number 7, 3, number 9, 3, number 11. Have a fabulous weekend. I'll see you next week.